In this video, we're going to be discussing factorial experiments, which is a type of experiment where we're studying not just one independent variable or one factor, but multiple factors. And we're just going to talk about two factors today, but this would extend to as many variables as you want to study. So these are really nice when we're actually doing research because very often, I don't just want to look at the impact of one thing on a particular output. I want to look at the impact of multiple things and see how I can really customize something. So, for instance, if I'm running an advertising campaign, I might have three different types of ads I want to run, but I also have different mediums that I could use. I could use mail, I could use a billboard, I could use email or some kind of an online board system where I'm showing my potential clients this. So I don't just want to figure out which of the ad campaigns is the best. I want to figure out which method of delivery is the best. And these things can happen all the time in the real world. And the term Factorial ANOVA is the analytical method that we use to deal with this. Now, to deal with this, we have to realize that we're going to have a whole bunch of people in factor A and a whole bunch of people in all the different levels and a whole bunch of different people in factor B. So if we draw this out, we're going to get this kind of a square, and I'm just going to do two levels in each. We'll call this factor A with two levels and factor B with two levels. And then I might have 1, 2, 3, 4, 5 individuals in each grouping. So we're only going to talk about a balanced design. That is, each cell or each combination of factors has the same number of individuals in there. But it is something important to consider that you cannot have this. In any way, this is the type of thing that we're going to be looking at. And it is important to realize that for these 5 people, they got, let's say, advertising campaign number 1 on the web. And for these 5 people, they got advertising campaign 1, but got a mail order version. So factor 1 level 1 and factor 2 level 1 would be these 5 individuals. And again, when we're talking about like generic levels and generic factors, it's kind of confusing. But when we jump into it, just realize that for all of the levels of each of the factors, we need all the levels of the other factors. So all 3 ad campaigns need to be offered on the web and in mail, or in this case, the 2 different types of ads we could run need to be offered both on the web and hard copy mailed to be able to run a factorial experiment. Now, this is going to look very similar to our previous experiment, except now we have, instead of just the alpha component, the sums of squares for the treatment there, we have multiple things. We've got the first factor, the sums of squares for the first factor, the sums of squares for the second factor, and the sums of squares for where they interact. Now, interaction is a pretty complicated topic that we're going to talk about maybe a little bit later. We'll try to do a quick example of what interaction is practically, but other than that, we're not really going to touch on it. Just understand this is a rather important and complex topic that we're breezing over for the sake of being able to run these two-factor experiments and analyze it using two-factor ANOVA. Actually, this might be a good time to discuss ANOVA naming conventions, and this isn't really on the slides anywhere, but you'll hear the term one-way ANOVA and two-way ANOVA. The number of ways is the number of factors. So one-way ANOVA would be what we've been previously doing in this lecture with just one factor. This that we're talking about right now would be a two-way ANOVA with 2 factors. You can do a 3-way ANOVA with A, B, and C factors, 3 different independent variables. After that, we just tend to call it factorial ANOVA, where we have multiple factors that we're taking into account in the ANOVA. So if you hear me say one-way ANOVA or two-way ANOVA, realize that the number of ways is the number of independent variables. And then lastly, we have a sum of squares error as part of our sum of squares term. And just like before, the sum of squares total can be broken into these. Now, the derivation of this one, I showed you how we could break out the sums of squares by hand earlier. One of the reasons we took so long to do that is because it's one of the only places you can do that nicely. Deriving this one is a really big pain, and even the sums of squares calculations are going to look pretty yucky. So we're going to look at them, and you'll see that the book actually starts to go back to the notation that we wrote by hand earlier, because it starts to get confusing using the shortcuts the book did earlier. So if you liked the notation earlier, you'll like this now, because again, it'll connect pretty strongly. All right, so within factor A, we have little a number of groups. So let's say factor A was the number of advertising campaigns. If we had 3 advertising campaigns, little a would equal 3. Factor B is the number of groups in little b is the number of groups in factor B. So if we had 2 modes of delivery, then little b would be 2. A minus 1 is the degrees of freedom for factor A, B minus 1 is degrees of freedom for factor B, and the degrees of freedom for the interaction is multiplying the degrees of freedom for factor A and factor B together. So A minus 1 times B minus 1. The total degrees of freedom is the number of groups in factor A times the number of groups in factor B times the number of replications in each cell minus 1. So in our previous example where we had 5 people in each cell, R would have been 5. That's the number of replications. The new ANOVA table, we have factor A, factor B, the interaction, and an error term. You'll see the degrees of freedom are just as we described earlier. The mean squares error is going to make sense. It's just the sum of squares divided by the degrees of freedom, just like we had before. The interesting part is the f-tests. Notice that to do a test of factor A, we divide the mean squares of factor A by the mean squared error. To do the test of factor B, we divide the mean squares for factor B divided by the mean squares for the error, and so on. So the f-tests are just taking all of the mean squares or the mean squares that you're interested in and dividing it by the mean squared error, and that calculates your f-value, and then you can calculate the appropriate p-value from there. Now to calculate the total or all of the different sums of squares, we use these equations. Now these are going to be the same kinds of equations that we had when we wrote this out by hand, and again you'll see that the textbook is starting to use that notation that we had. In this case, x sub I, j, k. I is the number of levels in factor A, j is the number of levels in factor B, and k is the number of replications within that particular cell, and then x bar bar is their grand mean. That's the mean of everybody. So each data point minus the overall mean squared for all of the data in all of the groups in factor A and in factor B. For sums of squares for factor A, we do the number of levels of factor B times the number of replications times the group A mean minus the grand mean squared. For factor B, we do the number of levels in factor A, the opposite factor, times the number of replications times the B group mean minus the grand mean squared. And then for the interaction, we have this lovely looking equation, the number of replications times the average within the cell. So remember we drew out 4 cells with 5 individuals in one of the cells. We take the average of those 5 individuals, subtract the overall average for that particular column, so that level of factor B, minus the overall average for that particular row, the mean of factor A, that level of factor A, and then minus the grand mean, and then we square all that. So all this is very, very yucky to do. Again, software is going to calculate it, though it is important to know how to calculate by hand if you need to. And then after we find all of these, I mentioned a trick earlier in the videos where you can use the sums of squares to calculate the SSE. This one is a very yucky looking equation too. Actually, the SSE isn't too bad. It's not a really yucky looking equation. It can be kind of a pain to calculate though. But instead of taking a pain to calculate that, we can just take the sums of squares total and subtract all of the other pieces to get SSE. And you can verify this through looking at the original sums of squares total equation. So for doing an example, now I really, really don't like the way this data is set up. I really don't. So one way that I might set this up is I might just include this as a single block. If I wanted to write it out this way, this would be a second block. And then we'd have 3 replications within, so yeah, let me kind of draw this out. There, that looks a little bit, well, it doesn't look particularly good. but you can at least see what's going on. This is industry I, this is industry II, so industry 1, industry 2. Then we've got 3 replications for industry 1 in Cincinnati, 3 replications for industry 1 in Cleveland, 3 replications for industry 1 in Columbus, and then 3 replications for industry 2 in Cincinnati, 3 for industry 2 in Cleveland, and 3 for industry 2 in Columbus. So this is a kind of this would be the wide format way of listing this. The long format would have a couple of variables, industry, then it'd have city, and then it would have wage. And so the first entry in this would maybe be industry 1, Cincinnati, 1210. Industry 1, Cleveland, 1180. Then maybe for this entry it would be industry 2, Cleveland, 1260. And that's how we would write this out in long format. I think that'd probably be a little prettier than this, but at least you can see what's going on. One nice thing about this is you can quickly see that within each cell here we have 3 replications. So I've got 3 workers in this particular city and in this industry for each one of these. And again, the fact that all these have the same sample size, the term for that is balanced. So real quick, I have R equal to 3. Just starting out from this, the number of replications within each cell is 3. Now factor A is industry type. There's 2 different types, so this is going to be little a is equal to 2. Factor B is location. Little b is equal to 3. And again, we have each condition repeated 3 times. Now factor A, I do the calculation and I get a p-value of 0.06. So because that's bigger than 0.05, I determine that the industry type is not a statistically significant factor in determining the salary. Factor B, I get a p-value of 0.03. I compare that to 0.05. It is smaller than 0.05, so this one is significant. Put a little star next to the significant one here. So because that is statistically significant, I determine that the location does have a statistically significant impact on the wage, and then the interaction is not statistically significant. Incidentally, if the interaction is statistically significant, you should stop your interpretations of these and assess the interaction. And actually, on that note, I'll go to the chalkboard quickly and discuss what a statistically significant interaction means from that perspective. So a statistically significant interaction really means that the interpretation of one variable depends on the other. So let's say we're looking at math grade. And we're breaking this down by, let's say, hair color, brown and blonde, and by sex. We'll have a blue line for male and a pink line for female, just for fun. So how this could look is that females, both brown and blonde, could be stronger than males, both brown and blonde. This could also look like females are weaker than males, both brown and blonde, in their math grade. But the trick that we're looking at right now, let's say, oh, and then what would it look like if blonde were better? So if blonde were better, it would look something like this, where we have the blonde scores, oh, excuse me, where we have the blonde scores, darn it, there, where we have the blonde scores being higher than the brown scores. And if the brown was better, then it would look like this, where the brown scores are higher than the blonde scores. Now, incidentally, we can have 2 things happen at the same time. That is, the brunette scores can be higher than the blonde scores, and males can be better than females. So this would be the case when both of our factors would be statistically significant. And if they weren't statistically significant, what this would look like is that there wouldn't really be a difference between male and female, and there wouldn't really be a difference between brown and blonde. Okay, so what is an interaction? An interaction literally means it depends. So what does it depends mean? Well, let's say I took my male line and brown was definitely better than blonde on the male line. But let's say on the female line, what this looked like was that I had not brown being better than blonde, but blonde being better than brown. This is what my female line looks like. So when I ask, are males better than females? Think about what your answer to this question would be. Are males better than females? Well, males are better than females if you're a brunette, but if you're a blonde, males are worse than females. So are males better than females? This is factor one. The answer to are males better than females is it depends. It depends on what your hair color is, and vice versa. So if I'm looking, is brown better than blonde? Are brunettes better than blondes? Well, the answer might be, well, if you're a female, then blonde is way better than brunette. But if you're a male, then brown is way better than blonde. So in that case, it also depends. The interpretation of the factor and whether it's meaningful or not depends on the level of the other factor. This is the very definition of a statistical interaction, and why, when we have a statistical interaction, we can't just say males are better than females or brunettes are better than blondes in terms of math grade. What we have to look at is we have to sit down and graph it out, because the definition of a statistically significant interaction is there is no overall answer. The answer depends. That is, the answer for one factor depends on what the other factor is. So that's a really quick breakdown of our statistical interaction. Here we can talk through the conclusions that we already made, that the wages do not differ by industry type. Again, P was greater than 0.05. We found our F value is bigger than the F cutoff value. We found that mean wages do differ by location. P was less than 0.05. And we found that the interaction was not statistically significant. Again, we already walked through the p-values of these conclusions. In the next video, we'll discuss the randomized complete block design. That is a design that's going to be very similar to our factorial experiment, but we're actually going to have a limitation on our randomization that's going to create a special way to look at this, specifically one where we don't actually look at the interactions.